nanofabrication. So we are able to tune the material properties by processing parameters, right? But in a bulk, for bulk materials. What about nanostructures or nanomaterials? And as you are aware, nanomaterials can have drastically different material properties. You can significantly enhance some of the properties, be it mechanical, electrical, magnetic, optical, or thermal. You can actually make some of the material like super hard materials or super strong materials or super elastic material, whatever it is, you can amplify. That's because when you are at nanometer scale, you can actually control atom by atom, meaning you can really tune the crystal lattice and atomic interactions, so you can amplify um, any desired property you want. But whereas in bulk materials, that might be slightly difficult. Okay, in bulk materials, you apply some external environment so that the material takes the shape of what you want it to happen, right? But whereas at nanoscale, you can literally arrange atom by atom. Okay, so that's what we are going to look at, which is nanofabrication or nanoprocessing in this class. So, okay, let me, come on. So now, can I quickly ask you what type of nanomaterials? Yes, I mean, we can do nanofabrication, but for what? To get nanomaterials, right? So what kind of nanomaterials are you familiar with? Microchip is an application of nanomaterial, which is made from a kind of nanomaterial, which is, it has a specific name. So you remember in the hard disk drive, how the disk had multiple layers I showed? So what is that? So it's 150 nanometer thickness, 100 nanometer thickness, couple of nanometer thickness. But what is that? So what are the types of nanomaterials? Thin film. So that is a thin film. In ICs, you use a thin film. What are other nanomaterials? Yeah, quantum dots, quantum wells. Yeah, quantum dots are basically nanoparticle-like. Yeah, and what are other kind of materials? Nanowires, nanoparticles, nanowires, thin films, nanosheets, nanorods, nanodiscs, and many, right? So now whatever shape you get, you put nano to it, and you get nano. Um, so here, thin films, you have, again, within thin films, you have different types of thin films. If you have multiple layers, then you have heterostructure thin film, you have monolayer, single layer thin films. Epitaxial thin film means all the material is in specific crystal orientation. Non-epitaxial, which is like polycrystalline. Then we have nanoparticles, And within nanoparticles, you have homogeneous nanoparticles, and then you have core shell nanoparticles. There is core, which is different material, and then you coat it with some other material called core shell nanoparticles. Then you have nanowires, nanodiscs. This is my favorite. There are you and shish kebabs. Okay, this is apparently a shish kebab nanostructure. So yeah, so you get, and there's a real paper on that one. Okay, so there are different type of nanomaterials, but joke aside, yeah, I'm not too familiar, but I just found it interesting. Yeah, um, I'm sure there can be many things you can. Yeah, it's a nanorod with a nanoparticle attached at multiple locations. Yeah. So now making these nanomaterials is not a easy task. You may make it. I mean, it exists in nature. Sometimes you have it by simple processes, but to identify that it is nanomaterial and to make sure you consistently get that kind of nanomaterial is expensive, and it needs a lot of heavy infrastructure. Okay, so now in thin films, uh, yeah, in thin films, so you have again several varieties. Okay, so how you make a thin film? Again, thin film or thick film. What is thin film? It's if you have 100 nanometers, it's thin film. If you have 900 nanometers, now you are in the boundary of thin, thick film. Anywhere, anything above 1 micron, it's a thick film. Okay, 1 micron or above becomes thick film, and of course, if you make it 500 micron, now you're almost into bulk materials. Okay, so but thin film is about, if you're talking about less than 100 or less than 500, that's what we call thin film. There are several ways to prepare thin films. Um, one I talked about yesterday, right? Uh, which is spin coating. If you use a high surface finish wafer, is like silicon wafer or glass, and drop any solution and spin it at 10,000 RPM, then you can get 100 nanometers. And faster you spin, thinner you get. Okay, so and again, that depends on the thickness and the speed relationship depends on the material, which material you are using as well. Okay, so but the thin film fabrication can be mainly divided into physical vapor deposition technique, chemical vapor deposition, and then solution based. And this is somewhat inexpensive, but because it is inexpensive, you can also um, you may not be able to get good quality thin films, which means they may not be epitaxial, okay, or they may not be even continuous. Sometimes they may be discontinuous. Okay, so things like screen printing, wherein you can coat up to um, few millimeters using screen printing, but a really good screen printer can go up to uh, maybe less than a micron. Okay, there are then spin coating is another one that is quite widely used, and then sol gel is a chemical reaction process, which is in a not so sophisticated environment. So this is solution-based chemistry. Um, there is also spray pyrolysis. So, and then you have physical vapor deposition, which is by physical phenomena. What that means is you either evaporate the material, or you use a laser to ablate it, or you use some electron beam to or some ions to eject the atoms from a target. Okay, so this is physics based. This is a physical vapor. You either use thermal, just heat it up, or you use a laser, or you use an electron beam, or you use ions to uh, eliminate, eject atoms from target material, and those atoms go and deposit. We'll see some of them. Okay, and then um, so need good vacuum. I mean, all of these, especially these, I mean, even this good vacuum, but these ones need very high vacuum. We're talking in terms of 10 to the power minus 6 torr, which is 1 torr, 1 atmospheric pressure. No, I'm confused. Is it 750 torr is 1 atmospheric pressure? But anyway, so these ones, um, 10 to the power minus uh, 5 uh, or 100,000 atmospheric pressure, meaning high vacuum. Okay, and these also need high vacuum. Um, this is here you use physical phenomena, thermal, light, laser, which is electron or ions. Whereas here you use chemical vapor deposition. Here in a high environment, you bring in two um, two solutions or two gases uh, mixed together and form a material. We'll look at some of the examples of chemical vapor deposition, which is called as CVD, and PVD is physical vapor deposition. So there is plasma enhanced vapor deposition. Then there is atomic layer deposition, which is ALD, quite popular. And that one you can deposit atom by atom. That is a chemical vapor deposition. Here you need good chemistry. So that means make two chemicals come together, make a reaction inside a chamber which has high vacuum and which has high temperature control. So that will give you a thin film of the resultant chemical reaction. Okay, so whereas this is uh, using physics or physical phenomena. So these are different types of thin film deposition. So it's not very responsive. It's, so so you can't do it in a shop, what we call here as a workshop. You can't use these nanofabrication in a machine shop because there will be lots of particles. It has to be in a clean room, and clean room is called clean room. And clean room has to be devoid of dust or any sort of particulate matter. So it has good air filtration system. The temperature is always kept at 20 degrees in some countries, 25 in other countries. Um, and they are classified. There is a classification system for clean room, 1,000 level or a 10,000 level. 1,000 level means there's only 10,000 particles per 1 meter cube. Yeah, 1 meter cube, I think. Again, I have to verify. So there are different classifications of clean room, and basically you have to. There should not be any particulate matter, and if there is particulate matter, what's the size of the particle? Few Yeah, few microns, right? So if there is a particle goes and sits on your film while you are depositing it, what happens? You get a discontinuous film. Okay, and imagine if you're growing an axial film, meaning all crystals aligned in one axis, right? So it has to be well controlled if it's axial, meaning it's like a single crystal thin film, right? If you're growing a single thin film, you don't want any fluctuations of any impurities or any dust particles, right? So it has to be very clean environment, and so people call it bunny soup, and you have to because even your skin molecules or hair follicles or anything like that should not come out. So your shoes need to be covered. You have to suit up, and it's always kept under a negative pressure. So particles are always sucked out. Okay, any floating particle, if suddenly a particle detaches from something, and it's always sucked up. So it's always a negative pressure. Okay, so the pressure outside will be higher pressure inside in these clean rooms, and it will be one door and then another door. First, you have to enter into one door, so that this is how you minimize pressure. Um, you know, you're making air gushing, changing the pressure suddenly. So there will be two doors to get into that. And for two doors, also there will be one more room to suit up. Okay. So um, has anybody used a clean room? Yeah. Where have you? Okay. Yeah. 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 So yeah, it's a similar setup, except that the pressure is kept at negative level, and then there are different classifications to clean room. 1,000 level, 10,000 level. 1,000 I think is the cleanest, and as you go 10,000, it becomes a little more dirtier. Um, I wouldn't call it here, but there will be some partic particulate matter in acceptable if there are 10,000 per meter cube. Um, okay, so that's uh, clean room setup. Uh, and normal clean rooms, you also have, because usually we use uh, deionized water for everything, washing, or there'll be ethanol bottles, deionized water, uh, a system to make deionized water, so on and so forth. So that's where a lot of natural fabrication and microfabrication happens. Give up. So now, when you deposit thin film, you have to deposit on something, right? So you can't just get a thin film that's 100 nanometer. It has to sit on something, right? So if it has to sit on something, then the atoms that you are depositing or molecules you're depositing go and sit on another layer, right? Atoms, right? So now there is a large mismatch in atoms of the substrate, the atoms you're depositing, what happens? So usually atoms too, if there is a van der Waals force, the center of each atom tries to align, right? But if one is really big and one is small, and then you have more atoms. So you are basically doing is you're creating some residual stresses between layer top the top layer and substrate. If they are similar atomic radii, then there won't be individual stresses, or there won't be internal stresses in the thin film. You saw the video of dislocation movement, right? So if atomic arrangement has a missing layer of atom, what happens? Wherever there is missing atom, there is a stress concentration, right? Just like that, if there is an atom arrangement, if the atom on top is much smaller compared to larger atoms at the bottom, then you start to introduce stresses. So it's very important to match the atomic radii of the substrate to the film you are depositing. Okay, silicon is the most preferred, but if you are depositing silicon, if silicon wafer, that means you are restricting yourself to only some of these atoms here. So you have to move away from silicon wafer if you have to use it hafnium, tantalum, or tungsten, okay, or platinum, gold. So you have to match the atomic radii between the substrate and the your deposit. Okay, so these are the sizes are in picometers, and yeah, so pico means 10 to the power minus 12. So these 880 meters, that means it's 8.8 angstrom. Okay, so this is 11.1 angstroms. Is that clear? So how it? So now we are coming directly to the PVD, that is physical vapor deposition. Okay, so CVD or PVD. CVD stands for chemical vapor deposition. PVD stands for physical vapor deposition. V is common. That is, you have to make vapors. So in using or physical parameters to make vapors, and the way we do here, this is the operation where we basically heat the material. Okay, so we heat the material to temperature. We don't completely at a closing temperature. You start to see atoms ejecting, as this is vacuum, right? So in a vacuum, the atoms to take off towards because of diffusion. There is no density here, density, and it's vacuum. They try to take off. Then you put a substrate right above target, you get deposition. This is thermal evaporation. And then E-beam operation. E is electron operation. So you generate electron beam filament. Could be some tungsten filament. There are many ways to generate electrons, and you generate the electrons, generate them. And also you use some magnetic points to direct where you want. So you direct the target. Target is if you want to deposit, for example, lithium or gold, platinum. And, uh, so lithium, gold, platinum, or copper are electrodes, right? You want to deposit electrodes on any wave, then you put that as a target with the source. Okay, and then electrons that are generated. So if you have to generate electricity. So here also, when you heat, so these are not somewhat expensive equipment and expensive processes. Okay, so you electrons come and hit the source, and the uh, you can use shutter when you don't want deposition, or when you want to stop deposition. You can use a door, basically shutter, to stop electrons going in, the vapor coming up. So the vapor um, uh, is ejected from the target, goes, deposits on the wafer or the substrate here, and the substrate keeps rotating so that you get uniform deposition. And you can monitor the deposition by a QCM deposition monitor. QCM is, does anybody know what is QCM? It's quartz. Oh, I forgot. Um, it's quartz crystal microbalance. So quartz crystal microbalance is a nice. You have heard of quartz, right? So quartz is it's a what material? Piezoelectric material, right? So quartz crystal monitors the thickness. Can you think how? What is the property of quartz? Sorry? Yeah, it vibrates when you apply AC field, and if if it is vibrating, then it generates AC field, or if you apply static pressure, it generates DC voltage. If you apply DC voltage, it changes its size. So now, can you think how it can monitor the thickness? It can tell you what's the thickness here. So you use quartz crystal microbalance to. It's really nice. It, you can literally see how the thickness keeps increasing in nanometers as the time passes, and it's the voltage that is come. The thickness is related to the frequency of the oscillation. I already gave the clue, but anyway, so let's come back to that one, but a little later. But so these are the two processes. I'll show how that works. So this is thermal evaporation, and this is E-beam. In here, in E-beam, we use electron, and in thermal, we just heat the substrate, heat the target, and we deposit the material on the substrate. So you can deposit varieties of elements and compounds using these techniques. And normally, you heat the substrate to some high temperature so that the deposition or the addition is good, and then you can use up to 500 millimeter substrate, means you can use 50 centimeter, half a meter substrate. That's quite big. So those are, you can deposit large materials, and so the excellent line of sight of site deposition, meaning you deposit it directly above the target, so you get a good deposition rate as well. Okay, so let's quickly look at how quartz crystal, right, one of our functional material, is used to tell what is the thickness of deposition. Is it up? Yeah, thank you.
A quartz crystal microbalance, or QCM, is a highly sensitive device that measures mass changes on a quartz crystal surface. A QCM is widely used in physical vapor deposition to monitor film thickness and deposition rates. The QCM is positioned in sight of the source, but not to shadow the substrate. The quartz crystal vibrates at a certain resonant frequency when it is electrically stimulated, which changes as the mass of the crystal changes. This vibration can be around 6 megahertz or 6 million full vibrations per second. A quartz
I mean, you won't realize its importance until you start until you start depositing yourself. So I showed solar cells, right? We had to deposit electrodes on top of the solar uh, photosensitive dye or photosensitive pigment. So we have to have certain thickness. If it goes beyond certain thickness, then there will be other complication. It peels off and so on and so forth. So we had to literally monitor. And if you are using thermal evaporation, the deposition rate is so much. So here, frequency change, because when that something resonates at its resonance frequency, what happens if you add a little more mass to it? Yeah, the resonance frequency decreases, right? The bigger materials will have lower resonance frequency. So it's as the resonance frequency reduces, that is calibrated to thickness. You can also hit zero because it keeps increasing and you don't take out the crystal and clean it, right? So when you start, it has certain resonance frequency, so you hit that is your zero thickness. And you start we don't have good control over when you start to both for e-beam lithography or e-beam evaporation or for thermal evaporation. Because once you heat, the atoms start to get ejected from the surface, and you can't control that because that is a difficult process to control. But what you can do is you can shut off, put that shutter on top of the target. So whatever vapors are coming do not go to the substrate. So, but when do you want to press that shutter? That's monitored by this. So we literally keep looking at it, and if it is thermal evaporation, the curve is going really fast, and we target, I need only 100 nanometer. And when it hits 80 nanometer, we press it, and then it goes to 90, 95. But if we press at 90, it overshoots. So it's really indispensable. It's very convenient way to. Otherwise, what you do to determine the thickness of the film? How do you know it's 100 nanometer? Uh, yeah, but so yeah, how do you determine the thickness? Well, I'm not sure which insulating material you're talking about. Well, what if both are conductors? The deposition, the substrate is also conductor and the film is also conductor. And if they have the same conductivity, right, that may not be possible. Though, other way, what you do is you take out the film, put it in a scanning electron microscope, and look at the cross section, and it will tell you. I mean, you can measure the thickness of the film, right? That is, but then you have to take it out, break the vacuum. Once you break the vacuum, it takes another 5-10 minutes, depending on the system. Some systems can take well over 1 hour to get, if it is 10 to the power minus 9 torr. In some equipment, you need 10 to the power minus 9 torr, which is high vacuum, it's called ultra vacuum. So for those, you need to pump for 1 hour to get that vacuum. So if you break the vacuum, you have to wait for another hour, right? So instead, a quartz crystal, it's really inexpensive. It's nothing but sand, form of sand, not sand, right? So quartz crystal can monitor our thickness. There is another equipment called ellipsometer that also measures thickness. You can use scanning electron microscope or ellipsometer or TEM, whatever high magnification microscope you have. You can't use optical microscope beyond for 100 nanometers. Okay. So yeah, this is really useful tool. It's just a quartz crystal. How to go? Okay. Okay. So that is, so we saw thermal evaporation and E-beam evaporation, right? So those are two physical vapor deposition techniques. Now we have another vapor deposition technique called slightly more sophisticated. It's not just heat up or put electron beam. It's called sputtering deposition. Okay. In sputtering deposition, what you do is you create an inert ion, usually through some inert gas. You can also create inert ions with oxygen as well. But a lot of the times you use argon. So you take argon and make it, you charge, you strip away an electron and it becomes positively charged. And these positive charges are accelerated towards the target. Target is kept at very high voltage, negatively charged. Okay, so when you have positive charges, you make positive ions, and you have a cathode that's at a very high voltage. There is a large force between the positive charged ions and the negative charged cathode electrode, which is nothing but the target. And they go and hit. When they hit, they knock off atoms from the target. The target is what you want to deposit. It could be silver, gold, platinum, iron oxide, whatever, rhodium. It could be a compound, not just element, gadolinium silicide, whatnot. Yeah. So, and then when you knock off these atoms, they they fly off, and you, right in the path, you put a film that you want to deposit. So the particles come and deposit on the substrate um, that is in the pot. So that is sputtering deposition. And we talked about E-beam operation. So E-beam, it's the voltage you need for generating electrons is about 10,000 volts you need in order to create the electrons. And you use different metals or different materials to create electrons. That is sputtering. This is E-beam operation. We also saw E-beam operation in the previous slide. Thermal operation, sputtering, E-beam operation. These are physical vapor depositions. Okay, so in sputtering, you can get epitaxial deposition, but in thermal operation, you may not get epitaxial. Again, depends. There are different levels of thermal operators, and E-beam also similar. You can get the epitaxial film, or you may not get epitaxial film, meaning the film that you grow might be polycrystalline in thermal or E-beam. But sputtering, you can get a epitaxial film which is aligned at certain crystal orientation. Okay. So here is a sputtering video.
So exactly how does the sputtering process work?
That's
First,
the chamber.
your coating materials are placed on a magnetron in a solid form called a target. For highly pure coatings, you need a clean environment with only materials of your choosing. This is why the chamber is evacuated, to remove almost every molecule from the chamber. Then, the chamber is backfilled with a process gas. Process gas species are chosen based on the type of material to be deposited. Common process gases include argon, oxygen, and nitrogen. Now the conditions inside of the chamber are ready to begin the process. A negative electrical potential is applied to the magnetron, which is the cathode, and the ground reference is the chamber, which is the anode. This electrical potential will cause free electrons to accelerate away from the magnetron. When these electrons collide with a process gas atom, they strip the gas atom of an electron, creating a positively charged process gas ion. The positively charged ion is accelerated towards the magnetron. This ion carries enough energy with it to knock off some of the magnetron's target material. This target material will then collect on surfaces in the path the magnetron is directed at. This is how material collects on your substrate. The positively charged ions will recombine with free electrons to create a neutral atom again. The light from the plasma is created when the ions recombine with free electrons into a lower energy state. When a free electron recombines with an ion, it has a voltage. The ion needs less voltage, so this excess voltage is let off in a light. The light is the plasma glow that is seen during processing. This process repeats at a constant rate until the desired thickness is achieved and power is removed from the cathode. This amazing atomic reaction is what makes Semicore a leader in custom vacuum.
Okay, so that is sputtering. We call it magnetron sputtering because you use what is called as magnetron that both generates the electrons as well as it's a cathode that attracts the positive ions, either argon, oxygen, or nitrogen. Then the other technique is called pulse laser deposition. So pulse laser deposition, as the name suggests, it's a laser and it's pulsed, right? So laser, as you are aware, can have very high energy. And the energy can be so high that you can literally ablade metal surfaces and take out particles of a metal. Okay, and depending on the type of the laser, you can take off large chunks of materials or fine particles. Okay, so the particle size depends on the resolution of the laser. So if it's very small, then you get smaller particles out. And of course, you want a smaller particles. But the pulse laser deposition usually gives you a particulate type of deposition on your substrate. Okay, it's not epitaxial um, like sputtering or e-beam lithography, but you can anneal it and get epitaxial film. Okay, so a laser, uh, again, you have to maintain 10 to the power minus 6 torr vacuum. A laser goes through a glass window into the chamber, hits the target, and the target is what you want to deposit. It could be anything. It could be a compound, element, whatever it is. And the fume comes out, the vapor comes out and hits the substrate. Again, you make sure here you can't put a shutter here, but you put a shutter here. Okay, when you want to start the deposition, you open the shutter, the fume starts to deposit on the substrate, and when you want to stop, you stop the you put the shutter. Okay, so you can use, one of the nice thing here is it can be a low temperature process, because the fume can you can generate fume with the laser itself has the energy, so it creates melt pool only in that small area it hits, and that fume comes out. So you can have deposition at low temperature in this. So you can put polymers inside here to get the deposition. You won't damage polymers. Okay, so so getting an epitaxial layer with PLD is quite tricky. You have to play with so many parameters. You have to, if you want to get epitaxial, you can't have low temperature. You have to increase the temperature of the substrate, and you have to increase the energy of the laser, and so on and so forth. So you can either use a nanosecond laser or a femtosecond laser. So the nanosecond laser is when its frequency is nanoseconds. The frequency of femtoseconds is 10 to the power minus 12. Okay, so not frequency is 10 to the power minus 12. The time per cycle is 10 to the power minus 12 seconds. Okay, so nanosecond or femtosecond laser, or they are different. In nanosecond laser, what happens is you ablate the material by local heating. The laser heats up. Whereas in femtosecond laser, it's completely different phenomena. So what do you think happens when you take a laser and put it on on any material? You excite, so the laser is nothing but photons, right? Photons go and hit the electrons, and electrons go to a larger or higher orbital with the high energy absorbed from the photon coming from the laser, and then they immediately fall back to the ground level or ground state, which is where they are supposed to be. And when they go up and come down, what happens is they release a phonon. And phonon is nothing but the vibration. The phonon is what results in heating. Okay, so the vibration, the phonon it generates in the material, heats that material in that place. And this is very local. We're talking in terms of few microns. Okay, so that's That's how nanosecond laser works. The phenomena in femtosecond laser is slightly different. What happens is when the photon comes and strikes the electron in an atom of the surface of the target, the electron goes to the higher orbit, but because it's femtosecond, before the electron tries to come back to the ground state, another photon comes. So because it's at high frequency, right? So almost 1,000 times higher than the nano. So before it comes back, another photon comes and puts it into the higher orbit. And before it comes back again, it keeps putting it into the higher orbit. So what happens if you're stripping electron from a material like that? You have nucleus that has all the protons, but you are stripping away lots of electrons from this atom. What will happen? So for example, let's say gadolinium 64, right? Its atomic number. It has 64 protons and 64 electrons. And if you keep knocking off electrons from gadolinium atom and you are left with only 50 electrons instead of 64, but there are 64 protons in the nucleus. So what happens? There's a charge imbalance, right? It's not sustainable. So you get what is called as Coulomb ablation. It's because of the charge imbalance, you are knocking off, breaking the bonds. Okay, so that is called Coulomb ablation. And the previous one is purely thermal, where the phonon heats the material, whereas with the femtosecond laser, you are basically creating Coulomb ablation, or it's also called Coulomb avalanche, multi-photon interaction. They call it by several names. So which means there is no temperature change. So it's done at a lower temperature. You are basically using charge to ablate the or knock off the atoms. So nanosecond laser is high temperature, femtosecond laser is low temperature. So if you have really complex materials, say if you have five elements, say high entropy alloy or some gadolinium, germanium, silicon with some addition of some iron in it for some special application, right? You have really complex material. You don't want to change the phase of the material, but you want to deposit a thin film of that material. What do you do? Which process do you take? If you heat, remember this complex 5-atom or 5-element compound will change its phase, right? You want to retain the phase. So you want to have it a low temperature deposition. Femtosecond laser is the choice, right? So it's a lot of physics, right? But that's the physical vapor deposition. And yeah, we make use of cool physics phenomena to get what we want. So here are the parameters: 10 to the power 6 star deposition. For nanosecond, you need 200 degrees centigrade substrate, and you can also keep it at lower temperatures. So I used PLD, femtosecond laser, but femtosecond laser is expensive, high energy laser. I did not have access to femtosecond laser anywhere, and I just by fluke, I was talking to one professor in mechanical engineering department, and he was boasting about how he has a cool laser from United States Air Force, and it's on a loan. I said, oh, can I bring my material and deposit on a silicon wafer? He said, yeah. So I was a postdoc, and I had all the time in the world to do experiments. So I deposited uh, a thin film of gadolinium silicide, gadolinium silicon germanium that nobody had done before, because many people had tried. Because it's such a complex phase, any small temperature change disturbs the phase, and it's difficult to get back that phase. You can get it in the bulk form, but in thin film, nobody had deposited the giant magnetocaloric material in thin film form. And yeah, I was able to do that using femtosecond laser. So that's the cool feature of laser deposition, or femtosecond laser deposition, right? So here is, now I'm showing off all my films. So this was done in 2012, 13. So these are the films. And of course, you do EDX analysis. This is XRD, looking at different peaks, representing different planes. And of course, there is always some secondary phase creeping in, although it should be, because of this complex phenomena, there is still some charge. The charge still introduces some secondary phases. This is more stable phase, and that quickly forms. So it's difficult to get rid of this phase. And we had some small amount of this secondary phase, which is undesirable phase. And the main phase was the 5-4. Okay, so and these are the films. This is how they look. It's a, you see, it's a particulate deposition, and it is continuous, not epitaxial. Okay, so this is 240 nanometers. The highest is 590 nanometers, and some of the particles are 100 nanometers or bigger. Any questions about any of the physical vapor deposition? So probably right now you're thinking, this is, out of what I do. I mean, it's nowhere close to what I do. But this is determining what you use, like what phone you use, what, including the glasses, the kind of glasses you wear. This determines, these kind of techniques determines what you do. Because the phone that you're using is cheap and fast because we are able to deposit cool materials that respond to certain stimuli, or we can deposit transistors at a smaller size and higher density. That's because of these kind of techniques, we are all able to enjoy nice phone, nice media, and communication. Even in communications, when you are looking at phased array antennas, those are deposited as well. Chips, and of course, signal processing units, they all need ICs, and they are done with this. Okay, you may not work on it right now, but if you keep progressing in your career, you will. If you don't work, you will, at least when you get into leadership roles, somebody will be working for you who will be in charge of something like this. Okay, you need to understand. Okay, so now is this beast. This is really complex physical vapor deposition system. You can see, right? This is literally how it looks like. And wherever there are molecular beam epitaxy devices, I have not used one. And to use one, you need to be trained for 1 year or 6 months, at least 6 months, to make use of this equipment. Okay, so this is molecular beam epitaxy, really sophisticated. And this is not even used in industries. This is only in laboratories where you can say this, you can deposit certain material that has certain certain effect that can be used for something. Then engineers will have to work to see alternative techniques, right? So this is really, really complex. It has multiple heads, and it even has a read. So like the XRD peaks you look at, right? XRD system, a huge, big system. You condense that to a small system, and instead of X-ray, you use electrons, and you get certain patterns when it's reflected back. That is called read. And there is a read in situ machine within the chamber to make sure that what material is deposited is the material that you want. Okay, so it's very, of course, very expensive. Not many universities will have them, but if there is a very well accomplished professor who has lots and lots of grants, maybe. Okay, so that is molecular beam epitaxy. You can deposit monolayers of atoms, molecules, create new molecules of what you want, right? Sometimes molecules may not form in the bulk form, but they may form in nanostructures, certain molecules. It may not be feasible at bulk level, but they may be feasible at nano level, and that's where you can try it out. And the vacuum is 10 to the power minus 8 torr, which is very high vacuum. And once you break the vacuum, you have to wait for at least 2 to 3 hours to get the vacuum. And of course, the growth is very slow because it deposits atom by atom and molecule by molecule. Then comes CVD, which is chemical vapor deposition. Okay, as the name suggests, it's chemical in nature. You bring in two materials, create a chemical reaction, and the resultant reactant, resultant product will go and deposit on the surface. Okay, so let me quickly play this video.
Thank you. Hey, what a nice place.
What is CVD? CVD is a process where gaseous precursors react to form a solid coating on a heated substrate. Let's look at a typical example using a very simple schematic to explain the basic principles involved. The vessel in which the process takes place is called the reaction chamber. In this instance, we'll be coating a flat component with a metal coating, reducing the metal chloride with hydrogen. The first action is to heat the component to the desired reaction temperature, which can be anywhere between 200 degrees C and 2200 degrees C, depending on the coating and the component. Once the component reaches the desired temperature, we introduce a controlled flow of mixed reactant gases into the reaction chamber. In this example, we will show a metal being deposited from a metal chloride gas. The first gas is the metal chloride. The metal is shown as blue atoms and the chlorine as green atoms. The metal is combined with chlorine to give a compound that can be maintained as a gas. At the same time, we also introduce a controlled flow of hydrogen gas, shown as red atoms. We adjust the process conditions so that the mixture does not react until it comes into contact with a solid surface, such as the component. As some of the gas molecules come into contact with the substrate, they are adsorbed onto the component surface. They are held onto the surface through relatively weak localized attraction. This adsorption allows the two reactant gas molecules to react together. The chlorine and the hydrogen react together, creating hydrogen chloride waste gas, and the metal atoms remain bonded to the component. The waste gas is continuously removed from the chamber, normally using a vacuum pump, creating a constant flow of reactant gases into the reaction chamber and waste gases out of the reaction chamber. As the coating process initiates, the first deposits are localized. Over time, the whole surface of the substrate becomes covered. The coating will apply to all accessible surfaces, not just the top. For some coatings, and depending on the desired thickness, we can keep this process going to allow the coating to grow. For some thick coatings, we can even remove the substrate.
So you got the idea. So, but the caveat here is you need to have a gas of the metal you are depositing, right? Not all the time it is possible. You need to have a precursor that is gas of the metal you want, right? So, which is, again, you have to have two gases and then get the reaction, which sometimes it's easy, but not all the times, okay? So that is chemical vapor deposition. And here, this is plasma enhanced chemical vapor deposition. In plasma enhanced, you can keep the substrate at slightly lower temperature. Otherwise, you need high temperature substrate. Sometimes substrates have constraints. You can't take them to very high temperature. For example, if you want to deposit on polymers, you can't in chemical vapor deposition. So yeah, this is if you are depositing silicon here. This is SiH4, NH3, and N2, whatever. It will have three element reaction, and it will deposit silicon on top there. So this is how it looks like. It's so here is the differences. This is physical vapor deposition. Kinetic energy is used. Chemical vapor deposition, complete pyrolysis on the surface, which is basically chemical reaction on the substrate, and plasma enhanced chemical vapor deposition, which is a form of chemical vapor deposition, but you can go to slightly lower temperatures. Then this is the state of the art atomic layer deposition. Whereas molecular beam epitaxy is so complex, atomic layer deposition is so simple. It looks just like this. And you just open this chamber and you have a spinning mount. You put your substrate and you open this chamber, you have put two precursors. And again, the disadvantage is you still need to have a gas of the metal you want to deposit. Okay, that's still one of the disadvantage, but it's a very simple setup, and I think they're not expensive. We see College of Engineering has 3 of these. In Bolton also I used one. So in Bolton we did not have molecular beam epitaxy. We had molecular beam epitaxy in Iowa State. These are somewhat simple, but the initial cost is not that high to set up the equipment, but getting the precursor of the material you need is not all the materials will have precursor, first of all, and then second of all, if you want to deposit aluminum, you need to get a precursor of aluminum, and that precursor also comes in a really fancy stainless steel canister like that will attach to only specific equipment, so they sell it for a really high price. Basically it's a fancy CVD. Same thing, there is chemical reaction, but here it happens atomic layer by atomic layer. Small amount, they pulse it. Pulse means send the precursors, purge it. So they remove. When you pulse it, one layer of chemical comes, sits on the substrate. The van der Waals forces hold on the surface. You purge, use argon and push all the remaining material that's not attached. Okay, and then you pulse another chemical. That chemical comes and reacts to only the monolayer that is attached, and then you purge again. Send the argon gas and it goes off. So, and then you will be left with monolayer of a compound that is deposited, or any of the product of the chemical reaction that is deposited here. Okay, it's usually used for high dielectric constant materials. But it's also because it's chemical vapor deposition, it's conformal, means it can deposit to any smaller surfaces. I put too many videos. I don't know whether. Okay, let's, because I wanted to cover something else as well.
Atomic layer deposition, or ALD, was pioneered at ASM. It is a key technology used to build modern computer chips. Whether it's an advanced chip in your laptop, smartphone, or in a medical system, ALD is probably part of the design. Today's semiconductor chips aren't assembled from separate components. They're created layer by layer on a silicon wafer. With ALD, we can deposit one single atom-thin layer at a time. Here's how it works. First, a chemical reacts with the surface of the wafer inside a reactor chamber, creating a thin film. Then, any leftover molecules are removed by purging with an inert, inactive gas. Next, a reactive gas with the second element reacts with the film, and any remaining atoms and molecules are again removed by purging the chamber. And voila! You've got one monolayer of the desired material. By repeating the process over and over, you deposit precise layers of material that are the perfect thickness, even if the underlying
So here is the difference. So the physical vapor deposition, it's done by kinetic energy, vapor coming and depositing on the surface. Here, chemical vapor deposition is slightly conformal, but it can't go into complex shapes like this, whereas atomic layer deposition can go into all the complex shapes. So this is conformal deposition. That's why atomic layer deposition is preferred over. So atomic layer deposition is nothing but a fancy chemical vapor deposition, but this is more conformal. Okay. Okay, now next is, we did thin films a lot. Now nanoparticles. Nanoparticles, how do you, I think somebody here prepares nanoparticles. Is anybody working on nanoparticles here? Oh, you're, yeah, I thought you were working on, what particles do you prepare? What material? What kind of nanoparticles? Which what's the chemical, what's the material itself? What's the name of the material? Oxides of which metal? Perovskites. So perovskites nanoparticles. Okay, so nanoparticles can be done by vapor deposition. So the vapor that you get that deposits the thin film, instead of holding it on a substrate, if you put a liquid, so when the vapors come and dissolve in the liquid, what happens? The particles form, right? They don't make a film. They become particles. So you can do the same vapor deposition, but instead of a substrate, you hold a liquid bath, which is difficult to do, but we'll see. Or you can do laser ablation, or you can do gas atomization, electrical explosion of wires. There are, ball milling is my favorite, which is mechanical engineer's favorite. So you just use ball mills, high energy ball mills, and do it for long time at very high speed, and you get nanoparticles. But a lot of them will be amorphous because your net ball hits so much, the energy is so much. Now, then you start to use certain techniques, how to minimize the energy and retain the crystal structure and not make them amorphous. Yeah. So ball milling is a very simple technique, vapor deposition, and then there are chemical methods. These are also inexpensive methods where you can do co-precipitation, thermal decomposition, hydrothermal, and microemulsion. So these are all different chemical reactions. You can do it in a beaker in any room, not your lab. Okay, so it's very simple to do nanoparticles. That's why there are so many nanoparticles that are available. So, so that's pulse laser ablation technique. So you basically put a target in a liquid and send a laser, and when the laser hits the material, it removes the material in particulate format, and it's in liquid, so it doesn't deposit anywhere, and it comes dissolves into liquid, and then you can evaporate the solvent or use any other technique to remove the solvent and get the nanoparticles out. Yield rate might be small, depends on the energy of the laser. Very high yield rate if you use ball milling, right? So we did our nanoparticles using ball milling. But so nanoparticle work is dominated by chemists or chemical engineers. And if you submit a paper to a chemical journal by making nanoparticles from ball milling, they will reject it, even though you can get really good nanoparticles. But somehow it belittles the complex chemical work that they do to make nanoparticles, whereas we just, with the crude technique, prepare nanoparticles. This is another one where you make in wire explode. A gas atomizer is another one. Basically, you use high pressure to push molten metal through a small orifice into a vacuum. You get nanoparticles. Okay. And this is our ball milled nanoparticles, and you can again get different sizes. And we looked at so when we ball mill for more than an hour, it's completely amorphous, the black and red. Okay, so we have to use some media in between to absorb some energy back and retain. So we still had a lot of amorphous particles, but we also had large amount of crystalline particles. And then you use some size separation technique and get monodispersed nanoparticles within certain sizes. And here is the SEM image of the nanoparticles. Then there is chemical method. Again, I'm not too familiar with all the chemical methods. I haven't done myself, but I've used some that are prepared using chemical method. But this is inexpensive, easy way to make nanoparticles, but you need to have the knowledge of chemistry to make nanoparticles here. Okay, so I think I'll skip. These are the characterization techniques. When you have nanoparticles or nano or thin film, how do you know you have the right phase, right crystal structure, right morphology, right composition? Now you have to do a lot of characterization, right? So preparing is one thing, characterizing is another thing, equally complicated and equally important, right? So there are really complicated and sophisticated characterization equipment. One of them is, of course, XRD. You can use XRD to know the crystal structure. And yeah, there are all these. XPS is X-ray photoelectron spectroscopy. Then you have Raman spectroscopy. You have FTIR, that is Fourier transfer, infrared spectroscopy. You can also have UV spectroscopy or visible light spectroscopy. There are so many techniques that you can use to make sure you have the right morphology, right composition, right crystal structure, right dimension, right? Then there are many other techniques. You can also have atomic force microscope, transmission electron microscope. I haven't even completed it. And there are many more. There is scanning tunneling microscope. There is any other characterization device? Okay, I think we'll leave it at that. Characterization is a whole other beast. So I would like, this is a small homework for you guys. I really like this video, the story of a scientist who got a Nobel Prize is very inspiring. I would like you to watch that. This is not too long video. It's about 20-25 minutes. But it's amazing how this guy who hasn't accomplished much goes on to win Nobel Prize and goes on to change the way we see things. Literally, we see things, meaning the light. The LEDs, that white LEDs that we get today is because of this guy, single-handedly figured out. Okay, this is very inspiring story. Please watch it, and there is that assignment. It's not graded, but please do it. Okay, so any questions about nanomaterials? Come down? Yeah, I think so. I mean, it doesn't really matter. So as long as the energy of the part vapor is high enough, you can keep it up. But if it's not high, then you invert it. Uses gravity to come down. Okay, so the substrate, right? So there are two requirements. One is the substrate itself. What kind of substrate? That the first slide I showed, atomic radii. You have to match the atomic radii of the substrate with the atomic radii of the material that you are depositing. Okay, if there is a mismatch, then you have internal stresses that will change the property of the deposited film. The second one is you want to have not a jagged surface. You want to have a smooth surface of monoatomic layer, which means we are talking in terms of few nanometer roughness, which is silicon wafers are like that. Our glass might have 10 nanometer surface roughness. Yeah. Yeah, jagged. Okay. Yeah. Mm. Mhm. Mhm. So the deposition, if you want, okay, if you want monolayer deposition, single layer deposition, then that will not help you because that will make it very difficult to get a continuous layer. But if you are not worried about monolayer, if you want, say, 100 nanometer thickness, 100 nanometers means 1,000 layers, right? Then you are okay. If you have a bump of 10 nanometers, that's fine. Yeah. 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 Hmm. Hmm. I don't think so because as long as you whatever material you're coating is suitable for any CVD or PVD you're using, should be okay, right? But you are, it's not about whether it's CVD or PVD. You will start to see it doesn't matter whether you are chemically depositing or physically depositing. It's the temperature, it's the conformity, it's the location of your, if you are doing a tool bit, a drill bit, it has to be mounted this way, right? And then for that, some physical vapor deposition methods will not work, right? Because they won't deposit on this side. So it's constrained by your application rather than whether it's PVD or CVD. Yeah. And the other problem with CVD is you have to have metallic gas. Yeah. So yeah. Any other questions? Okay, I think yeah, we are ready for a tea break. Yeah. So, oh, next class, I'm going to completely deviate from functional materials. This is a favorite topic of mine, which is my current research focus, which is brain stimulation. Okay, and the reason, I mean, it looks completely different in the beginning, but the underlying requirement, or not the requirement in the current state, the vision that we have for getting new brain stimulation techniques involve complex functional materials. So for that, we need to understand brain stimulation. So, but it's a interesting topic. It's the hot topic now, and yeah, you will see. Yeah. Okay. So see you at 2 o'clock. I'll be around as well. So if you have any questions, I can answer.